Okay, so the second part, I'm not going to address today the questions about average atomic mass. I will make sure that those get addressed one way or another. Thank you for asking those questions, and I will, like I said, if I can't find the right video that someone else has made, I'll just make one and post it. But the second half of topic 2 is basically about electron configurations, about electrons in atoms. So not about the nucleus. We're kind of ignoring the nucleus other than as this little spot that everything wants to be close to because it's got all these positive charges in it. And we're going to talk about where those electrons live in that vast space between the tiny marble at the center of the soccer field and the ends of the soccer field, which is the rest of the atom, volume of the atom. So I introduced you to the Bohr model before, or reminded you about the Bohr model. We usually draw it as if we've got our little nucleus in the center, and then electrons around the outside. And we often draw it like this, as if there's similar distances between the different energy levels. When we draw a Bohr model, each of these rings, concentric rings around the nucleus, is what we call a principal energy level. All right? And they have numbers. They're numbered 1 through 7. Why are they numbered 1 through 7? How do I know that there are 7 of them? Yeah. Yes, so rows, the periods of the periodic table correspond to energy levels. There could be more. I mean, an electron could jump, I guess, theoretically past 7, but we're only going to talk about the 7 that we know about. Yes? You're thinking about the octet rule. We'll get to that in topic 4. Yeah. All right, so the closest one is going to be energy level 1. That's going to be electrons at the lowest energy level. This is like the comfy chairs in front of the TV when you're watching the Super Bowl that have little tables next to them for your snacks and your drinks, and lazy boy recliners. Everybody wants to sit there because you have the best view of the screen and the most comfortable chair. That's where the electrons want to be first. And then after that, once those chairs are full, there's no more lazy boys. Then there's a nice, row of, plush dining room chair, upholstered chairs. And they're pretty comfy too, but maybe they don't have the tables for the snacks and you don't get to recline. So they're not as comfortable, but they're better than having to stand up in the back. So if the lazy boys are taken, then you're going to take the comfy chairs behind the lazy boys. Behind that, maybe there's the piano bench, which is really not very comfortable, but at least you're getting to sit down and watch the game, and you still have a pretty good view of the screen. And then there's standing room only in the back, which is like the outside energy levels, which it takes more energy to stand up for the entire game, right? Unless you're a huge fan, in which case you're probably standing up anyway. But that's kind of the idea of these principal energy levels, is we want to be as close to the nucleus as possible because these are electrons, they're attracted to the positive protons. So n equals 1 is going to be our closest, and 7 is going to be the farthest away. And those electrons are going to have higher energy. Okay? And I will post these slides. Now, we often draw it as if the energy levels, these concentric circles, are kind of equidistant from each other, but that's not how it really works. The distance between energy level 1 and energy level 2 is the largest. That means the jump in energy is the biggest, going from 1 to 2. 2 to 3 is a little bit smaller, 3 to 4 is a little bit smaller, and so on and so forth. Part of that is because there's more geometric space for the electrons to be in as we get farther away from the nucleus. And part of it is because those electrons still want to be as close to the nucleus as possible. So they're going to crowd in as best they can so they can at least see the scoreboard of the game on the TV screen. Okay? Yes? That is a great question. I don't have a good answer for it at this moment. I don't know if that's a realistic thing or if that's just a... I don't think that's a realistic distance, but I I, well, because this is a representation of how much more energy it takes to be in energy level 2 versus energy level 1, or energy level 3 versus energy level 2. I don't know that the distance from n equals 1 to the nucleus is a realistic thing in this picture. But I will see if I can find that out, if that's real. It's more about and we'll see some other stuff tomorrow about sort of those relative energies. Okay, so we've got these principal energy levels with numbers 1 through 7. Right, they didn't include 7 on here. But there's probably because most of the elements in energy level 7 are synthetic, that would have electrons in energy level 7 at the ground state are synthetic. So it's probably most of the elements in the universe are going to only have up to 6. I don't know. I could be making that up for the reason, but it does go up to 7. Okay, so then within the principal energy level, we have sublevels. The principal energy levels get numbers. The sublevels get letters. So each letter indicates a different type of orbital. The orbital is the sort of smallest container for electrons that holds 2 electrons. The letters are S, P, D, and F, and those letters indicate something about the shape of the orbital and the position of the orbital. The S orbital is a sphere. It's the closest that the electrons in that energy level can get to the nucleus. So that's the lazy boy of that energy level, okay? That's going to be the lowest energy. The next sublevel is the P sublevel. And the P orbitals are shaped like these dumbbells, and there's 3 of them in the 3 different axes of orientation, X, Y, and Z. So we could call them PX, PY, and PZ. Why are the p orbitals shaped like this, such that there's only a tiny bit of it in the center and more of it on the outside? Yeah. Okay, yep, so that they can keep out of each other's way, for sure. That's why the different axes. But why don't they just glom around in the middle as well? Yeah. Well, yeah, so they're all electrons, and they're all negative, and they want to stay out of each other's way, right? Yeah, Brayden? Yes. Well, no, that's a little bit more about within an orbital. Yeah, Grace? Yes, it is like that, and it's related to that, although that's a little bit of the next level from when we start using those orbitals for bonding. But think about it. We've already got an s orbital taking up this center space. Okay? So the p orbitals are not going to want to take up that center space very much because the s electrons are going to be in that space. So the p electrons are going to be more likely to take up the space outside of the s orbital because that center space is kind of already taken, yes. Yes, great question. That is essentially a probability cloud. So I'm gonna skip to the next slide, but don't panic. You actually don't have to know most of what's on this next slide. This is an image. I don't remember how this data was taken, but this is essentially locations of an electron in a hydrogen atom, measured locations of an electron. And you can see that it's not a perfect sphere, the way that the picture shows it. But the majority of the times that we were able to locate this electron, it was within that space. So yeah, the orbital is generally, the definition is generally given as wherever there is a 90% chance of finding the electron at any given time. So most of the measurements were found within this space, and so that's generally speaking a spherical space. And so that's why we draw the model of the s orbital as a sphere. But yes, it's a probability cloud. It's not like the Bohr model is also called the planetary model because it looks like planets orbiting the sun, but the electrons don't orbit the nucleus in a strict path like that. They are constantly moving around and can be found at any one of these places at any given point in time. So the orbitals, the way we draw them, these sort of dumbbell-shaped or almost balloon shapes, that's a model, but it's based on data, okay? So the s orbital and the p orbitals are the only ones you have to know. You have to know that there are 3 p's and that they have a dumbbell shape. You have to know that each energy level has one s and it's a spherical shape. But you can see that in the same way that the p orbitals had to take into account the position of the s orbital, when we get into the d orbitals, they also have to take into account the electrons that are already present in the p orbitals. And so they have even funkier shapes. And then we get to the f orbitals, and they're even crazier. So you don't have to know what the d and the f orbitals look like. I just like to put this picture up to show you that it's wonky. And again, these are just models, but these are models based on data. Okay? So yes, it's a probability cloud, but we have a model for the shape of that probability cloud that is reasonably accurate for our purposes. Okay. So we've got these s, p, d, and f orbitals. Each orbital can hold 2 electrons. So if you look at page 10 on your study guide, there's a picture of the Bohr model that shows something similar to what I put up before with the increasingly smaller distances between the concentric circles. And then also this table. It only goes from energy level 1 to 4 because 5, 6, and 7 are just like 4. The first energy level is so close to the nucleus that it only has room for 1 s orbital and therefore only has room for 2 electrons. After that, we get a 2s orbital that is outside of the 1s orbital, so a little bit further from the nucleus, a little bit higher energy. That also has 2 electrons, and then the second energy level also adds a set of p orbitals. 3 p orbitals for a total of 6 electrons, so our second energy level can carry a total of 8 electrons. Third energy level adds the d orbitals. There are 5 of them, can hold a total of 10. So our p, there are 3 p's, there are 5 p orbitals, 5 d orbitals. And when we get to energy level 4, we have our 7 f orbitals. Okay. So as we're getting farther away from the nucleus, we're getting to have a bigger and bigger sphere, bigger diameter, more space, so we can hold more electrons. Okay. And then, as I said, 5, 6, and 7 have the same number as 4. Okay. Now, how on earth are you going to remember all these numbers? Like, if I asked you how many electrons can energy level 3 hold, how are you going to remember that it's 18? Well, there's a trick to that. And that is that the periodic table is organized by electron configurations. It is pretty awesome. It's one of the reasons why the periodic table is one of the best inventions of mankind. The first 2 columns, these are called groups, are what we call the S block. This is where our s orbitals are being filled as we go across a row. As we go, and then the rows are called periods. So as we go across a period, we are filling in electrons in one particular energy level. And the weird part is hydrogen and helium, because hydrogen is in the first group because it has 1 electron, just like these all have 1 electron in their respective outer energy level. And helium, even though it only has 2 electrons, because there's only room for 2, it has a full energy level. And that is a special thing that is true of all the elements in group 18, the noble gases. So that's why helium lives over here, even though its second electron is still going into an s orbital. But that's why there's only 2 things on the first row of the periodic table, because there's only room for 2 electrons. Second one, we have the 2s orbital, and then we have our 2p orbitals. There are 3 of them, so there are 6 elements here. We have our 3s, and then our 3p. Again, 2 and 6.